In our experiments on speech enhancement, we observed that a DNN trained with different kinds of noises give different speech enhancement performances on Chime4 dataset. So we wanted to understand the influence of noise on the network, and we also want to predict or explain how a model trained with one particular noise, if it can generalize well to other unseen noises. So the way which we went about doing it was using feature attribution methods, which tends to assign importance to each dimension of the input. For example, in an image classification task, for this particular image, it was to be classified as 7. These particular pixels were found to be useful. Different methods which are being proposed for feature attribution methods. In our work, we use DeepSHAP or Deep SHapley Additive explanation. The contribution of our work are threefold. The first one is we used DeepShape to provide importance values for speech enhancement models. So for example, if this is the input spectrogram and this is estimated mask, and if you want to obtain the feature attributions for this particular time frame, this is what the DeepShape value will give us. So this time frequency bins are important to estimate the values of mask at this particular time frame here. Once we have this feature attributes, we propose a objective measure called speech relevance score, which is the ratio of two quantities. For example, this is the input spectrogram, and this is the feature attributes for one particular time frame. The denominator here are basically number of time frequency bins which are above some particular threshold t, and then a numerator here are a subset of these quantities where the time frequency bins of this particular attributes should belong to speech, or in this case it's IBM or ideal binary mask. So the idea of this is that a model which generalizes well should make a decision purely based on speech and not on noise bins, because it doesn't have access to the noise profile in unmatched or in unknown noises. So finally, we use speech dispatcher to obtain generalization of speech enhancement models. To understand the generalization capability of a speech enhancement model, we train the model using two different kinds of noise. We refer to that as FSSN, which is speech shape noise, and F network sound, which is basically a model trained with what is referred to as network sound. So we evaluate the speech relevance scores under two conditions. One is matched conditions when the noise is known, and under unmatched conditions when the noise is different from what was used while training. And we find that these two models use very different speech relevance scores. One is better than the other, and we find that the model with which less difference gives better word rate, which validates the hypothesis made by speech relevance scores that the one with lesser difference gives you better generalization capabilities.